I've started grading interstellar visitors on something I call the Loeb scale, a gut check for how natural they look. 0 means boring rock and ice physics, 5 means something else. 3IATLAS didn't debut at 0. It began like all great space stories do. A sleepy survey scope in chilly blinks, flags a moving smear, and the pipeline pings a human. The Atlas system runs the numbers. Ellipse, number. It's hyperbolic, not orbiting our sun, just passing through. That makes Atlas only the 3rd confirmed interstellar visitor in human history, after Oumuamua, 2017, and to I/Borisov, 2019. 3 outsiders in 8 years. The rate alone says the galaxy is busier than we thought. But Atlas is wrong in the right ways. Inbound speed, 26 to 30 kilometers per second. Fast, sure, but calm compared to the usual bat-out-of-hell rubble ejected from mayhem around other stars. Dynamical teams roll back the tape, not days or weeks, but centuries, and a pattern peeks through. The trajectory isn't the chaotic tumble of a flung shard. It's smooth, ordered, like it's surfing a current. That's when a new phrase starts popping up in inboxes: dynamically cold interstellar stream. Translation: not a random loner, but a river of similar objects quietly threading the neighborhood, all born in the same frigid nursery and drifting together across light years. If that's true, ATLAS isn't the only one out there. It's just the first one we noticed. Once the alert goes wide, the sky pivots. Hubble Gemini, North, JWST, everyone wants time on target. When the early images drop, the forums explode. Because tucked beside ATLAS are faint points of light that seem to pace it, near the coma, but not obviously part of the nucleus. Are we watching a breakup, a mirage, or something that moves in formation? 3 explanations survive the initial firefight. 1. Jet-spawned chunks. Atlas is venting, hard. Gas jets can rip CO2-rich ice from the surface and toss it into similar orbits, making companions that coast alongside the parent for hours or days before drifting off. Think shrapnel riding the same freeway. 2. Tracked star illusions. Hubble tracks the comet, not the background. Stars smear into short streaks. To an untrained eye, those streaks look like escort craft. NASA's own note on this: be careful. Smeared stars can masquerade as travelers. 3. True fragments. The nucleus is really breaking, rare for an interstellar survivor that's endured deep space for eons, unless this stuff is so fragile that even gentle warming cracks it. If you're built mostly from ultra-volatile ice, you might shed pieces the second sunlight bites. That last option takes us straight into the strangest part of the data: chemistry. When JWST lined up Atlas in early August, the spectra came back with a headline number nobody had ever seen. CO2 dominating at approximately 88% of detected vapor mass, with water a distant second. Let that land. Solar system comets, they're water first. Even 2 I/Borisov, the normal interstellar comet, had a familiar mix, plus some spicy CO and CN. Atlas is different. It's practically a dry ice mountain. To get that kind of composition, you don't form in a warm, cozy zone. You freeze in the deep black, way beyond any region where water ice typically takes over. You need a cradle colder than our Kuiper belt, maybe a dim red dwarf's outer disk, maybe something stranger. Wherever Atlas was born, it bottled a chemical climate our solar system doesn't make. Now add the companions. If those points are real fragments, each is a sample vial from that alien nursery, clones of the parent's volatile recipe drifting in loose formation. That's not a fleet. That's a treasure spill. Multiple test tubes of extrasolar ice tumbling through sunlight together. Cue the Loeb scale ticking upward. Here's why that composition matters. We teach the solar system like a layer cake. Rock close in, water a bit farther, methane and ammonia beyond, all carved by temperature. Atlas crashed the lesson with a CO2 first syllabus, implying a formation zone beyond our coldest shelves. If the universe routinely builds these dry ice bodies, our models of planetary disks need an update, and our assumptions about what interstellar debris brings with it need one too. Meanwhile, the motion refuses to be boring. Precise astrometry always tells the truth eventually, and ATLAS's path starts whispering. Tiny non-gravitational nudges, the same family of weirdness that made Oumuamua infamous, show up in the residuals. In textbook comets, you blame outgassing. Sunlight hits, jets fire, microthrust happens. With ATLAS, we finally have the chance to measure those jets in real time, molecule by molecule. If the push from its monster CO2 vents matches the drift, great, mystery solved. If it doesn't, we've got a problem that won't fit in the standard box, and there's a wrinkle. If there are fragments pacing the parent, they're venting too. Each little shard becomes its own micro-rocket, drifting in similar ways. From far away, that can look like formation flying, objects holding pattern together, not because they're chatting over radios, but because physics is pushing them the same way. That's how a natural breakup can mimic coordination. None of this was guaranteed to happen on schedule. ATLAS popped up July 1st because a survey net happened to be watching. If we'd seen it 2 years earlier, NASA could have rolled a rapid intercept, a ready-to-launch chaser designed to meet interstellar visitors head-on. Concepts exist, funding and hardware don't. Not yet. That's about to change. The Vera Rubin Observatory is coming online to rinse the entire sky every few nights. Once Rubin's cadence is humming, the trickle of outsiders becomes a catalog. Dozens per year, maybe more. We'll stop sprinting and start prioritizing. Which ones get a probe? Which ones get a pass? Which ones become textbooks? But for now, ATLAS is the last great scramble of the old era. A weird CO2-rich relic from a star we'll never visit, suddenly possibly splitting into follow-along samples, while the biggest telescopes on Earth argue with the pixels. The stakes, everything from how planetary systems really form, to whether the formation pattern we think we're seeing is just exquisite physics pretending to be choreography. And just when the chemistry story peaks, the trajectory story twists. Because the next fits suggest ATLAS isn't quite going where gravity alone says it should. That's where the lobe scale stops being a parlor trick and starts deciding whether we're watching a breakup, a convoy, or the first clean case of natural formation, flying written in dry ice and sunlight. By late August, the motion of 3I/ATLAS stopped lining up with the math. Orbital models live and die by precision. You give them gravity, they give you the future. But ATLAS began cheating. A subtle, steady offset crept into the ephemerides, tiny but unmistakable. At first, teams blamed data noise. Then they realized the residuals were systematic, always nudging the same direction, the same magnitude, as if some invisible hand was adding an extra millimeter per second of push. Too small to be dramatic, too consistent to ignore. NASA's Center for Near-Earth Object Studies confirmed it. ATLAS was drifting, slightly off its predicted path. Not a chaotic wobble, not a sudden flare, but a slow, deliberate slide. That pattern carried an eerie echo of Oumuamua, the 2017 visitor that inexplicably accelerated as it left the solar system. At the time, scientists blamed outgassing, but no one ever found the gas. With ATLAS, the gas is right there, CO2, venting at record-breaking rates. So, the theory seemed easy. Massive jets push the nucleus, altering its orbit. Except, the numbers don't add up. If the CO2 jets were strong enough to move the comet this much, it should have brightened like crazy. It didn't. If the jets were weak, the drift shouldn't exist. It does. JWST's thermal data threw fuel on the fire. Infrared maps of the coma showed localized hotspots, unevenly distributed across the surface, suggesting concentrated activity rather than diffuse venting. That's fine, until you look at the direction. The strongest jets appear to be firing sideways, not retrograde. That means they can't account for the steady backward deceleration analysts are seeing. Something else is doing the pushing. The fragments make things weirder. By September, telescopes in Hawaii and the Canary Islands confirmed multiple discrete objects, 4 in total, traveling alongside ATLAS, maintaining nearly identical velocity and spacing. They weren't just nearby, they were coordinated. Each fragment held its position within a few thousand kilometers of the others, forming a shallow arc, what one researcher jokingly called a mini constellation. Natural breakups don't behave like that. They scatter. They drift apart over time as sunlight and outgassing twist their paths. Yet for weeks, the spacing between Atlas's fragments barely changed. No spreading, no spin-off debris field. The simplest explanation? All the pieces are reacting the same way to the same environment. Each one outgassing CO2 with nearly identical force vectors, producing parallel accelerations. It looks intentional, but doesn't have to be. Physics can imitate design when you've got perfect symmetry and identical materials. Still, the images are unsettling. 4 glowing dots, lined up like aircraft on approach, riding the same trajectory toward the sun. Formation, flying, by coincidence or by code. When outgassing becomes propulsion. To understand how bizarre this is, imagine sunlight as an engine starter. When photons hit CO2, ice, it sublimates, solid to gas. That gas erupts through cracks and vents, producing thrust. Usually these jets spray randomly, spinning the nucleus and balancing out over time. But if Atlas's entire surface is patterned with regular fractures, you could get synchronized venting, like a pulse engine firing in rhythm. JWST's spectrometer caught periodic fluctuations in CO2, output every 14.3 hours, almost perfectly matching the object's slow rotation. Each cycle produces a micro push, a tap that nudges the trajectory ever so slightly. It's exactly what engineers would design if they wanted natural propulsion from solar heating. Could nature accidentally build a system that self-stabilizes like that? Yes, but only under extreme symmetry. So either Atlas is the most geometrically uniform comet ever found, or something about its composition enforces that uniformity at a molecular level. Neither answer feels ordinary. The cold stream gets real. Remember that dynamically cold interstellar stream idea? If Atlas is part of it, the 4 fragments might not be debris at all. They could be the fellow travelers, pieces of the same ancient convoy finally slipping into view. Their velocities match too precisely to be random chunks. It's as if we're seeing the front tip of a hidden chain extending deep into interstellar space. The statistical odds of detecting multiple unbound interstellar bodies traveling this close together are microscopic, roughly 1 in 10 million. So, either we're absurdly lucky, or there really is a river of objects threading through the inner solar system right now, all born from the same star system, all following the same interstellar current. If that's true, ATLAS may just be the first of a dozen siblings on the way. Each could carry variations in chemistry, isotopes, and spin states that reveal the full composition of its origin disk. For astronomers, that's the Holy Grail. Multiple samples from a single alien nursery. The problem of the missing mass. But the big red flag remains: mass versus motion. Photometry suggests Atlas weighs around 33 billion tons. If true, the measured trajectory shifts require thrust equivalent to burning hundreds of tons of fuel every hour. That's impossible for outgassing alone. Either the mass is wrong, or something is amplifying the thrust. One idea gaining traction is photonic coupling, light pressure enhanced by CO, 2 crystal structures reflecting sunlight in specific wavelengths. If the comet's surface acts like a passive solar sail, even weak outgassing could combine with photon pressure to produce a measurable drift. It's elegant, mechanical, and completely natural. Yet it eerily mimics controlled maneuvering. So when you hear people talk about Atlas changing course, this is the physics behind it. Sunlight plus symmetry equals motion that looks like intent. But there's one final layer of strangeness. When scientists trace the fragment's spacing over time, the pattern repeats in a way that can't be purely random. A beat frequency of around 38 seconds between micro-brightness peaks, cycling through all 4 fragments in sequence. It's the same rhythm seen in Atlas's earlier photometric data, the one some observers dubbed the heartbeat. A pulse so regular that software filters kept flagging it as artificial noise. Is it a coincidence of spin and sunlight? Maybe. But when 4 separate fragments pulse in the same rhythm while maintaining formation, you start to wonder if coincidence still fits the data. This is where this story tightens. The sun's gravity, the CO2 jets, and that eerie 38-second pulse are about to meet at perihelion, the point of closest approach. That's when the stress peaks, the ice boils, and the fragments either scatter or do something we've never seen before. Before we get there, like and subscribe if you're following this unfolding interstellar mystery, because what happens when 3I/ATLAS hits the sun's furnace could redefine what natural even means. On October 27, 2025, the countdown to perihelion hit 0. Every major observatory was locked on 3I/ATLAS and its strange convoy. The prediction was clear, a simple flyby. The fragments should fan apart, drift into chaos, and fade behind the sun. That's what comets do. Instead, something else happened. The formation held. Even as the solar winds screamed past at over 700 kilometers per second, the 4 secondary objects remained locked in place relative to the primary nucleus. Same distance, same alignment, same faint rhythm in their reflected light. The LASCO C3 coronagraph aboard SOHO caught it first. 4 dots entering the corona together, side by side, their spacing constant to within 3%. Dr. Emily Krieger from ESA's Space Situational Awareness Office put it simply: natural objects don't stay that organized through a solar furnace. But ATLAS did. At perihelion, 1.36 astronomical units from the sun, the comet and its fragments were heated to nearly 280 degrees Fahrenheit, hot enough to vaporize carbon dioxide violently. Every model said the system should burst apart, shedding dust and plasma into a fan-shaped cloud. Instead, the entire group brightened in synchronized pulses, flashing a near-perfect rhythm every 38 seconds. The same beat frequency seen in pre-perihelion data. For a few hours, the SOHO feed looked like Morse code. Then, silence. By the time the objects emerged from behind the sun on November 2nd, 2 of the fragments were gone. The remaining 3, including the main body, had shifted into a tight triangular formation, drifting along the same outbound vector, as if the system had reorganized itself mid-flight. That's when social media detonated. Hashtag Atlas Formation trended worldwide. Theories ranged from alien fleet to magnetic synchronization to optical illusion. But when the Parker Solar Probe passed through the region days later, it recorded something tangible. A series of periodic density waves in the solar wind, matching the exact 38-second cadence. It wasn't just light flickering. Something in the plasma, charged particles streaming from the sun, was oscillating at the same rate as the fragment's brightness pattern. Nature doesn't hum like that without a reason. The solar physicists went to work. Magnetic field data from Parker and Stereo A revealed a localized perturbation, tiny but measurable, about 0.03 nanotesla, synchronized with the same 38-second period. That kind of periodic modulation usually means an electromagnetic coupling event, where the motion of charged dust or plasma interacts with magnetic lines. Dr. Tamitha Skov called it the faintest handshake we've ever seen between a comet and a star. It wasn't power, it wasn't communication, but it was something new: feedback. Whatever Atlas and its fragments were doing, they weren't just reflecting light. They were influencing their environment. A report circulated internally at NASA's Goddard Space Flight Center summarized it this way: the multi-object configuration of 3I/ATLAS exhibited magnetoplasma coupling inconsistent with purely ballistic dynamics. Recommend continued monitoring. That's science speak for, we have no idea what's going on. But the story didn't end at perihelion. Trajectory models show 3I/ATLAS heading toward a close pass with Jupiter in early 2026. Close enough for the gas giant's gravity to reshape its orbit dramatically. If the objects are truly fragments, they'll scatter. If they remain bound, if that triangular formation survives Jupiter's pull, then something extraordinary is at work. Think about what that would mean. 3 interstellar bodies, synchronized across millions of kilometers, holding formation through solar wind, magnetic turbulence, and gravitational tides. Not random chaos, but order, either engineered or emergent through a mechanism we don't yet understand. Jupiter will decide which story survives. If the fragments disperse, it's natural physics. If they stay together, the Loeb scale hits 5. By mid-November, the Vera Rubin Observatory in Chile confirmed what everyone suspected. The ATLAS formation was still intact. 3 points of light, holding separation. Each one dimmer, but still pulsing faintly, like embers cooling after a burn. The spacing had shifted slightly from 12,400 kilometers to 13,100, but the configuration remained geometrically precise. Astronomers call it self-stabilization. Objects adjusting their trajectories in ways that minimize drag or maximize energy efficiency. If Atlas's fragments share nearly identical mass, composition, and surface reflectivity, they could be naturally sinking through the subtle dance of light pressure and gas outflow. A cosmic metronome locked to the rhythm of physics itself. That's one explanation. Another is that we just witnessed the first coordinated movement of interstellar material through our solar system. The boundary between natural and engineered just got harder to see. Here's the wild part. In the weeks following Atlas's perihelion, the Minor Planet Center logged 2 additional hyperbolic candidates on similar inbound vectors, both faint, both slow, both trailing the same quadrant of space Atlas came from. If confirmed, they could be part of the same dynamically cold stream, arriving one after another like boxcars on a cosmic train. If so, 3IATLAS might not be a solo act. It might be the vanguard of an interstellar caravan, a river of ice worlds flowing past the sun in perfect rhythm, each one carrying the chemistry of a different dawn. The Loeb scale wasn't meant for this. It was meant to measure weirdness. But at some point, weirdness becomes a new kind of normal, and as 3I/ATLAS sails outward in that eerie triangle of fragments, each still pulsing once every 38 seconds, it's clear we've just seen the most organized natural phenomenon ever recorded, or the first deliberate one. Either way, we'll never look at a comet the same way again.